Notes on hydrogen fuel cells. It's interesting to note that the fuel has been developed through time. The percentage of hydrogen content in the fuel has increased. It seems the natural progression of the fuel in the future will be to hydrogen. Two principal reactions in the building of a hydrocarbon fuel are the formation of water and the formation of carbon dioxide. As hydrogen content in the fuel increases, the formation of water becomes more significant, resulting in the proportionally lower emissions of carbon dioxide. A wide range of organizations, from energy companies to automobile manufacturers, are working to develop the fuel cell and the accompanying infrastructure. A trend in the production of power is clearly visible. In the 19th century, there was the steam engine. In the 20th century, of the internal combustion engine. The 21st century may be the fuel cell. The fuel cell was developed in 1839 by Sir William Grove, a British scientist and lawyer, by accident. He was performing, electrolysis experiment. He disconnected the battery from the electrolyzer and connected two electrodes together. He noticed that the current flowed in the opposite direction, consuming the gas, hydrogen, and oxygen. His battery consisted of platinum electrodes placed on the test tubes of hydrogen and oxygen, immersed in a bath of dilute sulfuric acid. It generated a voltage of about 1 volt. However, Grove's fuel cell was not practical due to problems of corrosion and instability with the material. As a result, there was little research and development into the fuel cells for many years to follow. Here you can see on the left his electrolyzer where he had the battery hooked up, and on the right there he had taken out the battery and left the two probes connected, creating that gas battery. The next fuel cell was Francis Bacon. He was a chemical engineer at Cambridge University. He began his work around the 1930s. Somewhere in the 1950s, he successfully produced the first practical fuel cell, an alkaline fuel cell. It used alkaline electrodes instead of dilute sulfuric acid, and his electrodes consisted of porous nickel powder, so that the gases could diffuse through the electrodes to be in contact with the aqueous electrolyte on the other side. This greatly increased the contact area between the electrodes, the gas, and the electrolyte, thus increasing the power density of the fuel cell. And there's a picture of Bacon's laboratory in 1955. In the 1960s, NASA started using a modification of Bacon's fuel cell. They realized they could do this to supply drinking water on board as well as electricity for the Apollo space missions. They used an alkaline fuel cell that is still used today in the Space Shuttle Orbiter. It produced 12 kilowatts of electricity, weighed 202 pounds, and occupied a space of 4.6 feet cubed. The advantages of the alkaline fuel cell were the high voltage output, and non-precious materials could be used. The disadvantages, however, was the carbon dioxide poisoning. There is a picture of NASA's Space Shuttle fuel cell. Fuel cells are classified by the type of electrode they use. The different electrodes operate at different temperature. Low temperature fuel cells include the alkaline fuel cell, the polymer electrode membrane, and the sulfuric acid fuel cell. All of these fuel cells use hydrogen as a fuel. This hydrogen can be extracted from natural gas, biogas, methanol, or propane by the process of reformation. Hydrogen can also be created through electrolysis of water. The high temperature fuel cells include the molten carbonate, solid oxide, and direct methanol. These fuel cells offer the advantage that they can use either natural gas or untreated coal gas as a fuel directly without use of reformer through the process called direct internal reforming. A sixth type of fuel cell is the direct methanol fuel cell. It is also a low temperature fuel cell, but it can be used methanol as a fuel directly without needing reforming. The primary limitations to this direct method fuel cell is the low rate of reaction on the anode is very slow. This results in a very low operating output voltage. For certain applications, the direct method fuel cell may be ideal. In the mid-1980s, Billard Power, based in Vancouver, British Columbia, and working with a contract from Canadian Department of National Defence, made significant breakthroughs in the fuel cell. Working with Johnson Matthey in the UK, they developed the PEM fuel cell, which has had significant increase in power density. From the breakthrough, it was recognized that fuel cells could be made small, powerful, and inexpensive enough to replace conventional power technologies. California Low Emissions Vehicle Program, a program of the California Air Resources Board, has been a large incentive for automakers to develop fuel cell automotives. This program requires the beginnings in 2003. 10% of passenger cars delivered for sale in California must be zero-emission vehicles, called ZEVs. Automobiles powered by fuel cells meet these requirements. To date, 7 of the world's 10 leading auto manufacturers plan to introduce fuel cells automotives beginning in 2003 through 2005 time frame. Okay, I did not write these notes. I'm just reading them to you. The NECAR 5 shown here is a prototype automobile by Chrysler. This automobile is fueled with liquid methanol and has a top speed of over 90 miles an hour. In forthcoming years, there are plans for buses, trucks, and trains, all powered by fuel cell engines. 30 buses will be commercially introduced in Europe cities beginning in 2002. Electrical energy demands throughout the world are continuing to increase. In Canada, electrical energy demands is growing at an annual rate of approximately 2.6. In America, electrical energy demands is growing at a rate of about 2.4%. In developing countries, electrical demands is growing at an annual rate of almost 6%. How can these demands be met responsibly and safely? There are many problems associated with the building of new power plants, both financial and environmental. Fuel cells distribute power stations provide a solution. The fuel cell distributed power plant can provide high quality, reliable power. Depending on this type of fuel used, fuel cells power plants produce little to no emissions. Shown here is a prototype fuel cell distributed by a power plant recently developed by Billard Power. This particular unit was commissioned by BC Hydro Grid and provides 250 kilowatts of electricity, about the same amount of heat, fuel, and natural gas. This is enough power to provide heat and electricity to a community of 50 homes, for example, or to a hospital or a remote location school. Billard plans to introduce its first commercial fuel cell distributed power plants in 2003. Fuel cell power plants are also being developed by several manufacturers to provide electricity and heat to single-family homes. Fueled by either natural gas or propane, these fuel cell plants are able to power a home independent of the grid. Plug Power, based in New York, has developed a new fuel cell power plant that supplies 7 kilowatts of electricity heat using either natural gas or propane as its fuel. That has enough power to supply electrical demands of a modern, energy-efficient home. Initially, fuel cells power plants will be grid parallel. Eventually, they will be grid independent. Plug Power plants so commercially introduced this home power plant, distributed through General Electric in 2002. This is a small portable fuel cell that can power up to several kilowatts of electricity, portable enough to be used anywhere. A fuel cell is a device that through electrochemical process converts hydrogen and oxygen directly into water. This process, this produces electricity, is released in the form of electricity and heat. Chemical process electrolysis in reverse. Alright, so here is an example of a simple PEM fuel cell. The hydrogen and the oxygen enter through the top. Through the center is our polymer electrode that encourages them to combine, forcing the electrons to come up through the load where you need the power and then back out. And your output from both sides is the water. You have an anode on one side and a cathode on the other that encourages that electron flow. Here is more on that polymer electrode and how it works. If you want more information on the chemistry behind that, speak to your chemistry teacher. Membrane electrode assembly. There are two portions. Carbon cloth electrodes combined to each side of the polymer membrane. Yeah, I'm not reading it to you. You can read it yourself. More chemistry on it. Look, more chemistry. Characteristic curve for voltage and current, power and current. Hydrogen storage. If we compress it as gas, it takes 56 liters. If we cause it into a liquid, it's 14 liters. And if you go all the way to a metal, it takes 9.9 liters. You can see the storage reduces obviously by the type. Ways we can get it: fuel tanks using a reformer can give us hydrogen, solar panels, an electrolyzer can give us hydrogen, and there is development into algae to produce hydrogen. Renewable energy sources are useful because as long as the sun shines, the wind blows, or the rivers flow, there can be safe, clean, sustainable electrical power, where and when required, with solar hydrogen energy systems. We've already talked about different power sources. Benefits of fuel cells: they are clean, quiet, safe, efficient, sustainable, and modular. More benefits of fuel cells. You can read those yourself. Our fragile planet. We have the responsibility to mind the planet so that the extraordinary natural beauty of the earth is preserved for generations to come.